So I welcome you all. Last three videos we discussed on the application of the beams, right? So from the bar element and from the basic introduction, then we went through some examples and we checked with bar element, and then we went to the beam element, how to derive the stiffness matrix and how to assemble it, right? So then we discussed on the applications of the beam. So we only discussed where the particular load is taken at a node, right? So I told you guys it's better to have a node if you are a beginner. So introduce a node where you load acting, but when you have a UDL, it's not easy because load is everywhere, right? So there should be a proper way to deal with that, right? So so these are the previous videos, so you can check, the links are in the description provided, right? So links have been provided in the description as well as a comment if possible. So this is today's example, and we will basically going through to determine this statically indeterminate, so you know how to do it. So simply statically indeterminate means whether this structure, the external forces and moments can be or cannot be determined by the existing equilibrium equations. So in other terms, you basically have three equations. What are those? Sigma f vertically equals 0, and sigma m f horizontal around at any location is 0, right? Or the whole system, and sigma m about any point is 0, right? So these three equations are there. So probably you have vertical reaction here, vertical reaction here, and vertical reaction here, right? These are roller support, right? So if you don't know these support conditions and other things, please check my video on the even the moment distribution basic concepts video. All things are there. I have discussed very fundamentally, right? So here you have a bending moment, but you know the horizontal, there's a horizontal force, but actually there's no horizontal loading or any horizontal reaction from this. Therefore this is already not an unknown, this is a known because the value is 0, right? Because no horizontal load acting on it or any other horizontal reaction. Okay, so in that case we cannot use this equation as well, because to use it we have to have some loads, right? So you only have two equations and four unknowns. So four unknowns, two equations. So the statical indeterminacy is 2, right? Statical indeterminacy is 2, right? So that means we need two additional equations, right? So today we are going to move with the finite element method, right? So first important concept is how you should define the nodes. So the problem is, so let's say we want to get the reaction, so we should have a node here, we should have a node here, that's what we are solving. We should have a node here, that's okay. Now think about in earlier cases, already loads are acting at a particular node, but here you have some load distributed along the member, right? So it's not practical to have because everywhere is loaded, right? You can't actually have everywhere nodes everywhere, right? It's computation pretty expensive. So we need some simplification, so that what happens if we can represent these loads for a finite number of nodes. Because if we have a point load, we originally define a node under that load, so that load is taken by that node, right? But here you have some additional loading between two nodes, right? So what you need to do is you should consider the load corresponds, that means load uh, belongs to that node, right? So if I just draw it, you can simplify. If you have some kind of loading, approximately half of, I don't, it's not actually half, right? It's not a, that cannot be actually half, but sometimes it will be, who knows, right? That's what we are analyzing, right? So approximately this much of portion will be transferring to this location, right? And also this much of load will be transferring to this location, right? I'm explaining what happens actually, right? This load, so load always, keep in mind, load always find its shortest way to transfer it to the ground, right? So this part will move into this node, right? And this part will move into this. There's a fixed support originally, right? So doesn't matter, I draw how the load is applying, right? So think about this portion, right? So you have a total load. So let's say this is the load. I'm representing it using some value, right? So that load is actually acting at somewhere middle. So center of mass of this portion is somewhere else, right? So the in addition to the force, this will apply some moment, okay, to this part, right? And here as well. So this load, the center of mass of this load will be somewhere here. We don't know the distance still. Let's say y. So center of mass of this load, this part of this UDL will somewhere be here. Let's say Z. So in addition to the load, let's say P1, this is P2, this is P3, right? This is this is let's say P4. Okay, and we'll say W distance. Sorry, not W, because the load is also W. Ah, no, just so what actually happens is what it actually giving. So this load will be directly transferred to the node, doesn't matter, right? And in addition, it will create a clockwise moment of P1x, right? That part is, it does, right? It does to the beam, right? Loading, not the resistance from the beam, okay? Beam will generate, usually that's what we are analyzing, because load is try to deflect the beam, but beam giving the resistance, that's what we are calculating as the bending moment or any reaction, right? This is the opposite of that. What is given to the beam, right? Not the reaction, right? What is the load or the moment given to the beam, right? So this is the load directly given. This is the moment generated due to this eccentricity. This is the load directly given, P2. And this is the moment generated due to that. It will be anti-clockwise around this point. So, because there's also already a support, right? So what it does is like this. This is the very simplest idealization, right? So this load will be directly given to this, but it due to this Z, it will have a bending moment of P3Z, right? Somewhere like this, right? So something like this. There will be a bending moment, right? So this is the simplest idealization, right? So there's a bending moment which is due to the support, right, at the node. So that means we can represent this load even it falls between two nodes, right? We don't need to define nodes, right? Earlier I said it's okay for you to have a node underneath the load because that's essential to understand the concept. And for now we are somewhere between beginners from the advanced, beginners towards advanced, so we can know. So this is the concept, right? So it gives a load and a bending moment in this direction, right? So we have a goal actually. So what will happen to the beam? So when you actually solve the beam, so we have three nodes, right? So you will have a nodal force of, let's say I'm considering downward positive and clockwise positive, okay? So you will have a nodal force of F1, a nodal force of F2. This cannot be negative or positive, okay? Okay, that doesn't matter because don't worry on the unknown, but keep your sign convention as it is, right? Stick with that because that's very important in structural analysis. Structural analysis is easy. Sign convention is difficult, right? Depending on the sign convention, the entire thing can be complex, right? Even you might not be able to find where you did the mistake, right? So let's consider here will be the force F3. And here I will consider the total bending moment around this node will be M1, and total bending moment. You know actually what the total bending moment around the pin. It's zero because towards either side, it's equal, right? So you can check on the moment distribution video if you need to learn it thoroughly. So that explains everything. Okay. So and the pin also, the roll of an end roller, the total bending moment is zero, right? Because it cannot restrain the rotations, right? That's why theta is there, right? And at here you will actually have let's say v1, the vertical displacement is zero, right? We know that because it's a fixed support, right? And theta 1 is actually zero, and v2 is here zero. Why is that? It's a support, it has not sink down, right? So theta 2 will be there, right? Theta 2 is there, theta 2 is non-zero, right? And here v3 is zero. See here the v is vertical displacement, okay? Displacement. These are the displacements. Theta 3 is non-zero. Theta 3 is there, right? That's why M3 is zero, M2 is zero, total bending moment, right? So it rotates until the moment is released, right? So yes, you can. So this is the nodal force, right? This would be the output that you taken from the node using finite element method. But is this the actual condition now? No, right? Because in the earlier case you had originally represent the nodal everything using nodes, because the loads are only acting at the nodes. But here you have some loads where they are acting away from your node, right? So you have to bring it, but belongs to a particular node, right? And the bending moment, due to that, you will actually have, right? You will actually have. So if you consider this, so this nodal force actually represent, right? There is a reaction, right? So I'm considering the reaction also in this way. You already know that reaction should be in the other way, because my sign convention is I'll keep everything according to my sign convention. Okay, clockwise positive and downward positive, right? And there is a load given to this node as well. Let's call this P1, right? You know what is that, right? It's a given. So we need to mathematically idealize the portion of UDL which belongs to that node, right? That's acting on that node, right? It's not the resistance given by the due to that load, right? So, and you will already have a bending moment in clockwise direction, right? Due to this load, right? So you consider, let's call this M11. Let's call this M11. I'm running out from the names. Okay, that's why. So and it will, this is due to the loads, right? So I will draw it in another color, otherwise you will be confused. These are the reaction forces. Okay, reaction forces, and this is the reaction bending moment. Okay, this is the nodal, this is the outflow from the node, but it will not be the same as the reaction in this case, because you already have some thing on this node. Let's see that, right? So here you will have some M-1 reaction, and you will already have clockwise bending moment due to the loads, right? Due to the loads like this. Okay, this part and this part, right? P1x and P1, right? Okay, and so you can write an equation to the total, whatever happens, total. So this M1 plus P1x, So it's already in clockwise direction, should give you this M1, right? This is total nodal force. So this is the finite element output that you will be given, right? So it consists the moment. This is the actually MA, right? It is actually MA. This is actually MA and RA, right? So what I want to keep you, the finite element output is not the direct reaction, right? So you have some contribution from the load as well, because there was no point loads, right, in this beam, right? So in such case, this x is 0, right? So you will probably directly taking the reaction as if there's no loading in between the nodes, so this x is 0, right? So always your node is, so load is on top of your node, so that means your reaction is directly given by the nodal output, but here it's different, right? So you have to calculate the bending moment again using another step, right? And the reaction as well. So reaction right, reaction plus P1 would be the output given by the finite element method, right? This is the total force at the node, total moment at the node, right? So it consists the reaction plus the load which belongs to that point, right? So let's consider what happens in the previous case. So we had some nodal force actually, let's show this. Yeah, I have this. So you can see, so in the earlier case, we determined the reaction at A and B, right? So you can see at none of these points, you don't have any point load. What you did was, you provide a node underneath the load, that node directly consider that load, right? So you only be remaining with the reaction, a nodal force at this location, and it is equal to the reaction, right? And here as well. So whatever given by the reaction will be the nodal force, which will be given by the FEM output, right? So what happens if you place another point load exactly another point load exactly above the node? So then the thing I'm discussing happens, right? Because now you have, so when you have a point load on exact this node, right? So whatever given by, so that node is actually, so let me type for you. So you should be careful when you have a load on the node which is a support, right? You should be careful when you have a load on the node and that node is created at a support, because support already have a reaction and you are giving a load. So that total So what the FEM doesn't know that. FEM give you whatever the total load at that node, right? So now you have a load and a reaction. Usually this happens as a support, right? Especially you should be careful if you have a load on the support, right? Or especially if you have UDLs, this should come into play, right? That means you should have a component of the load as well as the reaction acting in this node. So the FEM gives you what the total force is, right? So that is the summation of the reaction plus whatever the load is given, right? And as well as that applicable to bending moment as well, right? So I hope it's clear. If you have any doubt, you can email me. I will give you the email. So, and where was I? Let's see. So you can determine if you know the total. If you take the total output from the FEM, right? Nodal force and the nodal bending moments, right? So that's not the reaction you need. You need to reduce these components to get the reaction you needed, right? Okay. So there's an official, maybe a standard way of doing. Some people doing like F plus. So this is the external loading plus R is now the total load at the joint is equal to K into D, right? So you need the reaction. To get the reaction, you should multiply these two and reduce the external load, right? This is the external load, okay? Load at that node, because this happens at a support, right? Why? You only have the reaction at a support, right? This will not come into play if you have a node in between somewhere in the beam. This will not come to play. You don't have any supports here. So you only have the external loading that is applicable to that node, right? But once you have a support, it will give a reaction. And if you have already a load, so this phenomena come to play. So keep it in mind rather than be a robotic, right? What is actually happening in the beam, right? So we'll go to the beam. So another thing I will show you. Before going to that, we usually take that load as a fixed end load, right? So how we are going to do that is, so you have some, sorry, you have a roller. Here you have a roller and the beam is subjected to a UDL, right? So the best approximation is you can take the fixed end loading and so fix everything, right? And take each portion. So you know this is applying WL by 2 load, and this is applying WL by 2 load, and this try to bend this beam in this fashion. That's WL squared over 2L. this portion, try to bend this part in this fashion, because when be like this due to the UDL. This is also WL squared over 2L, right? So this is, so be very careful. This is not the fixed end forces or moments. Why? This is what is given to the beam. So the fixed end reactions will be opposite to this. So beams, so the support should have a resistance of WL by 2. And support will have a clockwise resistance of bending moment of WL squared over 2L. This is what we usually deal in analysis. The external forces, right, generated. The resistance generated. WL by 2. And it should have a resistance in this way. WL squared over 2L. So, but in the finite element loading, so finite element method, what we are interested in, what is given to the beam, right? What is given to that node. So you should be very careful. It's exactly opposite to the fixed forces and moments, whatever in the appendix in the books, right? Because think about logically, what is given to the node, not the resistance generated at the node, what is given to the node. That's exactly opposite. Okay. So if it is, if this is anti-clockwise, this is clockwise. If this is upward, this is downward, right? The right. So for whatever, this is exactly one length, one, and this is W is also one. So you remember WL by 2 will be W is W, then this is 0.5 kilonewton, and WL squared over 2L will be 1 over 12 kilo newtons meter, right? So this will be same for each beam because the loading and the span are equal. If you want, you can go with different configuration, different node systems, maybe somewhere node at here, somewhere node at here, but the concept is same. So you fix it and calculate the nodal load acting on that portion, right? So if you consider this part, so this will give W load, W by 2 to here, WL by 2 to here. So this part is also giving node load to this one, right? And this part as well. So this will be WL by 2, WL by 2. There will be total W given into this node. And as well as there will be exactly WL squared by 2L in this way, and from this beam WL squared by 2L in other way. So the total is 0 because anti-clockwise and clockwise, right? So it will be getting cancelled and the moment will be 0, but this will have, so I'm repeating, this is not the support, so fixed moments of fixed reactions, right? Fixed reaction, not these, right? Fixed reactions are the exact opposite of this. This is what is given to the node, right? And I will draw it for you. So the value of this 1 over 2L, 1 over 2L is 0.083. the magnitude is exactly equal to the friction force, but it's not the friction force, right? That's the concept, right? It is what given to the uh, node when it is fixed, right? So basically, you will have that will give WL by 2, so that is 0.5 kilonewton, and that will have 0.83, that's 1 over 12, right? And this will have 0.083. Right? And what happens is, so this will give 0.5, this will give 0.5. So altogether this would be 1 kilonewton. This would be 0 because anti-clockwise and clockwise. So this will give 0.083 and 0.52 this location, right? So keep these things in remember, right? 0 and 0.83, 0.83, 0.5. These are the loads given to the nodes, right? So 0.083, 0.5 and 0.1, 0.83, 0.5, right? All in the, so this is anti-clockwise, okay? This is clockwise. So we will refer to the sign when we are working. So this is our working sheet. So the same things I will get. E is 210, I is 0.0004, L is 1. L means the length of the each segment. But if you have different segments, different noding arrangement where the length is not equal, so you can have L1, L2, L3 likewise, right? So it doesn't matter. You can anyway do that, right? So since the length is same, the stiffness matrix for each portion will be same, okay? So this is the stiffness matrix when I calculated. So this is 12 EI over L cube. So that's going to be 12. So EI over L cube is here, right? And into 12, right? So that gives you the, so I have already uploaded these things. So this is 2L, 2L squared, for instance, 4L squared into EI over L cube. So that what you have to do is 4L squared into EI over L cube. So you can determine the value of the stiffness matrix from here, right? This is for, so for this is same for element 1 and element 2, right? So at element 1, so we usually go in order. At any element, so vertical displacement is the first coordinate, and then vertical, sorry, the rotation is the second displacement, right? So v1 theta 1, v2 theta 2, v1 theta 1, v2 theta 2. That order is very essential, very important. So for the second segment, you have v2 theta 2 and v3 theta 3, right? So this is the stiffness matrix 1. So this is stiffness for first member K1, and this is for the second member, right? So now so basically those are same, that's why everything's same, okay? Why? Because for each portion, L is same, I is same, E is same, and then everything same, right? Stiffness, that does not depend on the external loading, right? If you If your loading does not affect this stiffness matrix, right? That's fundamental in matrix method of analysis, right? Stiffness or flexibility coefficients, your external loading does not affect, right? What is what does the stiffness gives you? The load caused by a unit displacement, right? F equals kx when x is equal to 1. F is k. That means when a unit, the force required to cause a unit displacement is called as the stiffness, right? So that's a fundamental meaning of stiffness, right? So what we're actually doing is we check the load caused by a unit displacement and we multiply it by the actual displacement. That's what we are doing. But if there is a displacement at B, let's say theta 1, right? Let's say theta 1. So that theta 1 is affecting each and every node. You can see this theta 1 is affecting each and every node. That's why we have components, right? So we cannot just say when you multiply theta 1 by that coefficient, it will exactly give M1. No, M1 is contributed by other factors as well. Like you can see, M1 is dependent on these four: V1, theta 1, V2, theta 2. So M1 is actually this into this, right? It's into this. So what happens is M1 will depend on V1, theta 1, V2, theta 2, right? So that means it is a function of displacements. That's why you need matrices, right? So what we are actually doing in this finite element is we check the stiffness, we get the force per a unit displacement, right? That is a standard, and then we multiply it by the original displacement. But we don't know the original displacement, right? That's what we are actually finding, and that we can apply boundary condition. For instance, so at the supports, we know the displacements are 0, right? We know the some displacement at fixed support, here it's 0. From that, we can eliminate from these and find the remaining displacements. And then again, plug it back and find the unknown forces. That's what we're actually doing. That's the grand summary of finite element method, right? So I'll show you. So this is the stiffness matrix for element 1, stiffness matrix for element 2. Now we need to assemble it. And you can see V1, so this will be the displacement in the entire global system, V1 theta 1, V2 theta 2, V3 theta 3, and that that is, so I will write this as also V like that. Okay. This is the matrix. Okay, this is the matrix. This is just to number these, notate these rows and columns. Okay, so you can see. So now you need, this is the global stiffness matrix, right? This is the global stiffness matrix. Okay, global is this. So this is element stiffness matrix, right? So from the global stiffness matrix, you can determine for instance this element, right? It's V1 row, V1 column, right? So you don't have, so just forget about this. Just forget about this one, okay? Just forget about this one for now, right? So we only have these two, right? We only have these two. So how to get this is, so you should consider V1 row, V1 column. We don't have V1 here, so V1 row, v1 column. So this is the element you need, right? That's v1 v1. Likewise, you can consider this element, let's say theta 1 theta 2, theta 1 row, theta 2 column. So theta 1 row, so theta 1 is definitely not here, theta 1 row, theta 2 column. So this is the element you need. That's how you construct the global stiffness matrix, and that happens to be a case when you have a common displacement. Say v2 theta 2 is common to both elements. So let's consider how to get this. Let's say, for instance, v2 column, v2 row, v2 column, this element. So you have v2 row, v2 column here, and v2 row, v2 column here. So what happens then? You have two components. Can you see the thing I'm highlighted in darker green, right? So then you have to add these two values. That's it, right? You have to add these two values, right? I think I have it from another function is somewhere else. So you need to add these two values, right? For this v2 theta 1, v2 theta 2, and you need v2 theta 2, v2 theta 2, this value and this value, right? When you add both, right? So this is going to be 0, right? v2 theta 2 this is going to be 0. That's why it is 0. So you can see this is actually, we are overlapping and adding the stiffness matrix, right? At the place where that is compatible, right? So this is our stiffness matrix 1. We overlap it from v2 theta 2 and add it, right? So when you add it, so this let's say, so when you add it from matrix 1, these four items will be added exactly as it is, right? That's the difference. When you add this one, it's this. When you add this plus this, it's 0. When you plus this, it is 0. This plus this, it is 6 something, right? So this is very easy, right? So all the other things are 0 because theta 1 v3, theta 1 v3 is not connected within a single element, so that is 0. v1 theta 3, and that's 0. So keep everything 0 first, then determine each value, right? If it is not related, that will finally be 0 as it is, right? As it is given earlier, right? So when I'm repeating again, when you want to make the global stiffness matrix, make everything 0, and then go each by each, v1 v2, because this is symmetric. So it's symmetric along this diagonal, so whatever is there is equal to this. That means f21, the matrix 2 1 1 2 element is equal to 2 1, 1 3 is equal to 3 1, 1 4 is equal to 4 1, 1 5 is equal to 5 1, right? First row fifth sorry, first row sorry, fifth row first column, and first row fifth column, right? So this is second row third column, and that should be equal with third row second column, right? Fij is equal to fji, right? That is so along the main diagonal you have a unique value, that is I equals to j, right? And now we need to solve this. So how we are going to do that is, so we know at A, V1 theta 1 is originally 0. Why? It's a fixed support. It does not allow translation or rotations. At B, it does not allow translation. So vertical displacement is 0, but there will be a theta, overall theta, okay? And V3, that is also 0, but theta 3 will be there, right? So there's now we can reduce this matrix like this. If it is 0, so from the other videos as well, you have to close that row and column. So theta 1 row and theta 1 column is closed. Theta V1 row and V1 column is closed. V2 row, because those are 0, the displacements are 0. V2 row and V2 column. V3 row and V3 column is closed. Right? So take into the matrix whatever is left, right? So left is these 4. You can see this is the matrix F equals, so this is the reduced stiffness matrix. So this is theta 1, theta 2, theta 3. The M2 and M3, I will show you how to calculate that. So M2 is, so in this location, so it's like this. Let me show you. M2 is like this. This is due to the loading plus everything, right? So we have to draw. Okay. So actually there's a total bending moment, right? This is the output from the output from the finite element method. So there will be some moment M1, a force in direction F1, right? Force in direction F2. And you know what is actually, so the total bending moment about the roller or pin or roller, whatever. So it's going to be 0, right? It's actually 0. You should be getting 0 because pin internal rollers or pin cannot restrain the total bending moment, right? So cannot restrain the total rotation. So total rotation. So there won't be any bending moment. So bending moment will be equally distributed over this part and over this part. So total bending moment is 0, right? We are considering the total bending moment. So at this point, you only have one member. So that total bending moment is easy. Then why it was 0? Because the contribution from the loading as well is 0, right? So if you recall it, so because your contribution from the loading is 0, right? This is MB actually, right? This is actually MB plus whatever P1 into P2, let's say P2 into Y, right? So I will call this P2 as load given by these and these UDL parts, right? So MB should be the bending moment. That's the MB we are taken from the analysis, right? So that is 0. Why? It's a pin joint, right? It's a pin joint. It's a pin joint. So this is, that's why this became 0, the FEM output, right? So because the loading contribution is same and equal, and that is also 0 now. This is 0 and this is 0. But here, this is equal to MC plus some contribution, P3 into, let's say, W. This is 0 MC because it's a roller, right? But this is not. Be very careful. This is not equal to 0, right? So you can take this as the nodal bending moment, right? This is not 0. M3 is not 0. M3 will consist of MC and the moment given externally by the loading. That loading is not 0 here because it's not a symmetric part as B. So that is also, if your node is somewhere else and this node is here, so you will have different moments, and then this will also not be 0, the total bending moment, right? This is the total. This is not the reaction, right? It's a special case, this becomes 0. Why? The contribution from the reaction MB is 0, and the contribution from the nodal component is 0. It is 0. And M3 is not 0, it is the contribution from the load, right? So that's going to be, you remember, 0.083, right? So that's in anticlockwise direction. Okay. So this is 0. And we will go to the, so I'll show you, this is 0.83 and this is 0. And the total W is 1, right? Given to the node. So I'm repeating it again. This is not the reaction because we have a loading contribution. If you didn't have loading on a node which is located at the support, then it will directly be the reaction as well. This is a special case, right? Repeating it again. And this is the total nodal output. And that consists of the reaction and whatever the contribution from the load, right? Okay, I think I did a mistake when saying that this is the reaction and then hence 0. It's not the reaction. So this is the total output. This is the actual reaction. Okay. XMC is the reaction. That should be 0. That should be 0 because it's a pin joint. Sorry, roller and roller. If it is a pin, that's also again 0, right? For this case, it's a roller. You can go to the Excel back and you can construct now the, so F equals KD. So this is actually 0.1/12. You remember that's in anti-clockwise direction, and you multiply it by 1000. Why? You need to bring it to Newton meter. It's in kilonewton meter, so you multiply it by 1000, right? And this is the K inverse, right? So how to get that is, K inverse is also 2 by 2 matrix. You select 4 cells. You select 4 cells. Check M in. So it will give you M inverse, matrix inverse. This is the array you need. Then Control Shift hold those together and then press, while holding those two, press Enter. It will give you the inverse, right? And you have to multiply this inverse by this F matrix to find theta 2 and theta 3, because F is equal to KD, K inverse into F is equal to D. So when you multiply that, so you need to multiply. So multiplication will give you 2 by 1 matrix. So select 2 by 1 cell, then M mult, array 1 is this. So order is very important. Then the second matrix, and Control Shift Enter. This is the displacements in radian, theta 2 and theta 3. Now we determine the displacements, right? Now we determine the displacements. So we actually have now displacement here. Okay. So unknown displacement for only those two, right? So we solve that. Now we have the stiffness matrix. So fundamentally that is the force per a unit displacement, and we have the displacements from each component. Now you can determine each and every force or any moment like that at the node, right? Nodal force. F1, M1, F2, F2, because F1 is, this order is very important. F1 correspond to V1, M1 correspond to theta 1, F2, V2, M2, theta 2. That order is very important. So you need to just multiply these two matrices, right? So I'll show you how to multiply. So multiplication will give you exactly this, like matrix 6 into 1. So I have to select 6 into 1 cells, then equal M multiply this. The second matrix is this, and control shift enter. So this will give you whatever the nodal force acting on that, right? And it's given that. So you can see the theta 2 is clockwise, we got positive, right? Clockwise moments and clockwise rotation positive. So theta 2 is clockwise, right? Theta 3 is anti-clockwise. It should be, right? Because this is going to bend this beam in this way. This is clockwise, and this theta is anti-clockwise, right? Then, so I'm getting F1 is in this direction, the total nodal force, right? Total nodal force is this. And you remember, you have now obtained these two, right? So you need to determine what's the reaction, right? So you need to reduce this part from this, right? So M1 minus this moment from the equation, and then F2 minus this from the equation, and that will give you the reactions in this is according to our sign convention, downward positive. Okay, so that will give you the total nodal force is downward, right? So nodal force is downward. Okay, so for VA, you reduce that total nodal force, you reduce how much? Whatever given by that loading. You remember it's 0.5 kilonewton. That's why I multiplied by 1000 to make it newtons, right? Okay, so from the total nodal force, so you remember MA plus nodal load is equal to F1, right? So we need, sorry, not MA, VA plus total node loading on that node is equal to total nodal load F1. So you remove that load from the total nodal load F1. That will give you VA, right? So actually VA plus 0.5 kilonewton is equal to F1, right? Remember? Then MA plus MA is acting on that way. You remember clockwise moment was there, which is given by the load, right? It is given by the load. So that is clockwise. You remember the value 1 over 12 kilonewton meter is equal to M1, right? So you need to reduce 0.5 kilonewton. So that means 0.5 into 1000 kilonewtons from nodal load. That will give you VA. And if you reduce 1.2 into half, why? To make it Newton meter. It's in kilonewton meter. That will give you this VB. So VB there was 1 kilonewton. You remember 0.5 plus 0.5. So you need to reduce 1 kilonewton. That means 1000 newtons. That will give you the reaction. And those are not in kilonewton meters. So you have to you have to divide this by 1000. To divide this by 1000. Divide this by 1000. This is anyway 0. To divide this by 1000. So now it's in all thing kilonewtons, right? So this is the reaction. So MB is, you can see 0 because the loading contribution was 0. Those are equal actually, right? You remember? Equal from both sides, 0.083 and 0.083 anti-clockwise and clockwise. So anyway, that reaction is exactly equal to the total nodal moment, right? So that is also 0. So for VC, you can see you have to reduce, and here you have to add because the here MC plus MC not plus. It's actually you are adding an anti-clockwise bending moment. You remember at C, K, and M because that load is in. I'll show you. This is in anti-clockwise direction, right? For clockwise is positive. This is what is given to the node, right? Anti-clockwise direction. That's why is so that's why you have to add. So you when you make this part to the right side, MC plus M3 plus this value, right? M3 plus this value 2000 to make it 100, and you divide it by 1000, right? Did I do a mistake? It's anyway 0, right? So yeah, NC should be 0. Okay, so because the reaction should be 0, right? MB should be the total reaction bending moment is 0 at B and C. So this will give you the reactions, the bending moment at A, B, C, right? So even if you want, you can check it from another method. Let's say matrix displacement method or matrix force method, right? These are the outputs in the reaction in kilonewtons and kilonewton meters. Hope you understand. If you have any clarification, you can contact me in this email. If you have any clarification, you can put an email to this. If you need any clarification, you can put an email to this. Okay, so I will be very happy to help you and assist you at any time. So you can contact me with using this. If you need anything to be sorted or any example to be done, you can send me this to this email, right? So thank you very much. So links are in the description for the previous videos. You should I think go through those to fully understand, right? So basically finite element is tough because students can't combine the theories well. I'm actually it took me around 3 years to combine these together, and then I thought of giving you for you to easily understand rather than struggling, right? So this will be helpful to you. I hope so. So thank you very much.